Hello everyone. In previous video, I had explained you the behavior of the function sine of 1 by x. So we had seen there the sine of 1 by x, this function which is not defined at x equal to 0, and its limit also does not exist. Sine of 1 by x, this function not defined at x equal to 0. Limit of sine of 1 by x as x tends to 0 is also not defined. It is neither continuous nor differentiable at x equal to 0. See, this was the graph of sine of 1 by x. As you approach towards 0, you had infinite number of oscillations, due to which the function is not having a particular value at 0. It is neither continuous nor differentiable, as well as its limit does not exist. Now let us see a case of the function when you multiply the same function by factor x into sine of 1 by x. Let us see what is going to happen. So when you have this function, this is the function f of x. Earlier we had a sine of 1 by x. Now we have multiplied sine of 1 by x by x. So now look at the graph of the function. X into sine of 1 by x is given by this graph. Instead of the band of values near 0, now it is having some convergent value. It looks like this. These oscillations are getting reduced. The amplitude of the oscillations getting reduced as you move towards 0, and they are converging to a single value. Means at x equal to 0, now the function is defined. It is having a unique value. You can substitute that here. F of 0 equal to 0 into sine of 1 by 0. Now sine of 1 by 0, it is a finite quantity. Though it is having some fluctuating value, the quantity is finite here, and 0 multiplied with a finite quantity is always equal to 0. That's why as you move towards 0, so the graph is going towards the value 0. Hence the function becomes defined now at x equal to 0. Earlier when you had the function sine of 1 by x, which was not defined. Similarly, at x equal to 0, you have to check the continuity of the function. Is it continuous? Those infinite oscillations, there were rapid oscillations occurring in this case. Now those oscillations get dampened, due to which you could define the value of the function at x equal to 0. So this x, the factor x, which is multiplied to the function sine of 1 by x, this acts like a hammer. Now this hammer dampens those oscillations and bring it to a smooth function. It is kind of now smooth function compared to the previous one. Previously the function was having very sharp oscillations, but now those get dampened due to this factor. This factor it acts like a hammer and it dampens the oscillations, and hence you could get the value of the function at x equal to 0. Now at x equal to 0, is it continuous? For continuity, you know that limit of f of x as x tends to 0 must be equal to f of 0. So now here again, limit of f of x as x tends to 0. You can have LHL as well as RHL. You can here limit x tends to 0, x into sine of 1 by x. Again the same argument here, 0 into some finite quantity. It is going to give you 0, and you will have here f of 0, which is equal to f of 0. Therefore it is continuous at x equal to 0. It was defined. Now it is defined as well as continuous at x equal to 0. Now what about the differentiability? Differentiability at x equal to 0. Let us see. Is this function differentiable at x equal to 0? So for differentiability, you need left hand derivative and right hand derivative. So limit as h tends to 0, the definition of left hand derivative, f of 0 minus h minus f of 0 divided by minus h. So this is equal to limit h tends to 0, f of minus h minus f of 0 divided by minus h. Let us substitute in the function. Limit h tends to 0, f of minus h means replace x by minus h, sine of 1 by minus h minus f of 0, we got it as 0 by minus h. Now this cancels, minus h cancels. Now you are remained with the factor limit h tends to 0, sine of 1 by minus h. Correct. Now you know that this limit does not exist. as the previous case. This does not exist, hence the function is not differentiable at x equal to 0. So it attained continuity, it attained the definition of the function, it got a specific value at x equal to 0, but it is not differentiable. Means this kind of smoothness, still it is not enough to define the differentiability. Compared to the previous case, the function became smooth, but still for differentiability that smoothness is not enough. Let us see what happens if we multiply this function with the factor x square. See, x square into sine of 1 by x. Compared to the previous one, now the graph has become more smooth. So there is a chance of differentiability. Let us check algebraically how it is to be checked. Okay. Now f of x equal to x square into sine of 1 by x. So f of 0, it is defined now 0, because 0 into some finite quantity. Sine value always lies between -1 and 1. Okay, therefore it has a range. So it is some value in between -1 and 1. It is a finite quantity. Now it is continuous at x equal to 0, as per the same argument before. Now what about differentiability at x equal to 0? So you check left hand derivative, same as before, limit h tends to 0, f of 0 minus h, I'll write directly f of 0 by minus h. So this is equal to limit h tends to 0, f of minus h, replace x by minus h whole square is h square into sine of 1 by minus h minus f of 0 is 0 divided by h minus h. So 1h cancels. Now as h tends to 0, so you know again now limit h tends to 0, it is minus h sine of 1 by minus h. So this is a finite quantity, h is tending to 0, so 0 into finite quantity, it becomes 0. Similarly, you can check what is r right hand derivative at 0, that also comes out to be 0. Therefore left hand derivative equal to right hand derivative at 0, hence the function is differentiable at x equal to 0. You can look at the graph, see how nicely it has become smooth due to the factor x square. Means I told you that factor x acts like a hammer. As you increase the power of the factor x, accordingly the power of your hammer also increases. It dampens the oscillations more and more, so that the peak of those oscillations get reduced and you will get a smooth curve. When you get a smooth curve, sudden changes are really less, due to which you can define the rate of change, you can define the differentiability at that particular point. So this function is differentiable at x equal to 0. It has the first derivative. If you once again check it out, you can see that it doesn't have the second derivative. Double dash of x does not exist at x equal to 0. You can check with that. Similarly, one more, x cube into sine of 1 by x. Look at the graph. It has become more smooth, hence it is defined at x equal to 0, continuous at x equal to 0. Similarly, it is differentiable at x equal to 0. First derivative exists. For this function, second derivative also exists, but the third derivative does not exist. You can check with that how the second derivative exists and third derivative does not exist. So this is how the sine of 1 by x behaves without this factor x and with the factor x, and when you raise the power of the factor x, how the function's behavior changes. I hope you understood this concept. Thank you for watching.